So, next we will see the characteristics of millimeter wave when it propagates through any channel. The main advantage of millimeter wave is its high frequency. So, we can increase the channel capacity to a few gigahertz, or even we can target 10 Gbps channel speed, but it is associated with some other problems like high atmospheric loss, high loss due to rain rate, then multipath effect. So, let us discuss this point first, then we will be modeling some channel and calculate link budget for a given millimeter wave line of sight system. So, millimeter wave first of all have high atmospheric attenuation. So, this curve we have seen in first class. This is the plot of attenuation in dB per kilometer versus frequency. So, the frequency scale is shown on top, starts from 10 gigahertz to 300 gigahertz, covers some part of microwave frequencies as well as millimeter wave frequencies. The corresponding free space wavelength is shown below. So, now if I follow this curve, we have two plots, one at sea level for attenuation, and the second one, the attenuation has been measured at a height of 4 kilometer from sea level. So, at sea level attenuation is higher, and we see that if frequency increases, attenuation also increases, and not only that, we have some attenuation peak. These are due to resonance frequencies of different types of gases. For example, at 22 gigahertz we have a small increment. It is due to the resonance of water molecule, water vapor, and at 60 gigahertz we have a peak. It is due to the resonance of oxygen molecule. Similarly, we have another small one at 118 gigahertz and another high peak at 183 gigahertz. Again, this is due to the water molecule, water vapor. So, we can't use all the bands for millimeter wave propagation. For example, if I want to use this 60 gigahertz band, then we will face very high attenuation due to oxygen resonance band. We have to use then these windows available in between two peaks for millimeter wave attenuation. So, these will give minimum loss. Another interesting thing, even if I look at these windows and compare the attenuation with that at microwave frequencies, we see that at 10 or 15 gigahertz, whatever attenuation we have, it is less than 0.1 dB per kilometer at sea level. But this attenuation, it increases to at least 1 dB, let us say above 118 gigahertz. So, at millimeter wave frequencies, even if we do not use this attenuation band, in between attenuation band also attenuation will be higher. But if we go high in atmosphere, in that case we can decrease the attenuation to some extent for satellite communication typically. So, millimeter wave has high atmospheric attenuation compared to microwave signals. Then rain fade, it is a serious problem. So, whenever it is raining in medium, in that case there will be scattering of microwave or millimeter wave signals by raindrops, and this scattering it increases with the droplet size. So, higher rain rate, it is associated with higher scattering effect, or in other words it will provide high attenuation. Now, when the droplet size is comparable to wavelength of the signal, propagating signal, we face maximum scattering. So, at high rain rate, typically at higher millimeter wave frequencies, we have very high attenuation. But one good thing is that if I compare these attenuation values with the attenuations whatever we have at millimeter wave frequencies, at infrared frequencies or at optical frequencies, millimeter wave attenuation is much smaller compared to them. So, at when it is raining heavily, in that case any infrared link or optical link it can fail completely, but millimeter wave link in that case also it can operate. So, sometimes we call, that is why a millimeter wave link all weather link or all weather system. So, next, surface appear rougher, so diffuse reflection increases. So, again surface, any reflecting surface, it is any practical surface, it is associated with some sort of roughness. Now, the RMS value of roughness, if it is much smaller compared to the free space wavelength of propagating signal, in that case we can consider it as a smooth surface and we will be having smooth reflection also. But at millimeter wave frequencies, where the wavelength is typically less than 1 centimeter, sometimes if I go to high millimeter wave frequencies, it is almost 1 millimeter. So, surface it will appear rougher and we have diffused reflection from wall and from the furnitures and from any buildings, foliage, trees also. Multipath propagation, particularly reflection from indoor walls and surfaces, causes serious fading problem. So, fading problem you might have seen even for a FM radio, you might have experienced. So, for example, let us say at this position you are getting a signal for your FM radio, but if you move 1 or 2 meter away, you are not getting any signal. Similar problem will happen for the millimeter wave, but in this case, since the wavelength is much smaller, just if you move your instrument a few millimeter, you may not get any signal. So, this is a serious problem. Doppler shift, another problem even at pedestrian speed, because Doppler shift it is proportional to velocity as well as it is proportional to carrier frequency, and at millimeter wave frequency carrier frequency is very high. So, even at pedestrian frequency the value whatever we will get it may not be negligibly small. So, we have to consider Doppler shift also. Millimeter wave it travels solely by line of sight and are blocked by building walls and attenuated by foliage. So, if you compare microwave signals, let us say at 2.4 gigahertz where wavelength is quite high. So, if any person he or she stands in front of any transmitter, then we have diffraction effect. So, you can say as if microwave signal bends around human body at lower frequency, or the blockage effect or shadowing effect we can say due to human body is negligibly small at lower microwave frequencies. But if we go to higher frequencies, then just like optical rays we face shadowing effect due to human body. So, if we place a transmitter behind me, so in front of me we do not have any millimeter wave signal. So, it is a problem for indoor applications, and not only that, it will be also attenuated by foliage. We have tree leaves, tree branches, twigs. So, all of them will attenuate or reflect millimeter wave signal. So, it has become a problem then for line of sight millimeter wave communication. So, maximum distance can be used, let us say just a few kilometer if we do not go to free space, if we consider a scenario on earth. So, it is a problem, but it also has an advantage that we can go for picocell if we think for mobile communication. So, same frequency component we can repeat just after a few kilometers without any interference. So, then densely packed communication networks through frequency reuse we can develop, and it show optical propagation characteristics. So, that means it can be reflected and focused by small metal surfaces, and diffracted by building edges. So, small wavelength, it allows modest size antennas to have a small beam width, increasing frequency reuse potential and small circuit size. Now, antenna gain, it is proportional to the physical area of the antenna in comparison to the wavelength lambda. So, if we have smaller wavelength, but if we use same area to realize any antenna at millimeter wave frequencies, it will provide much higher gain compared to at microwave frequencies. So, we can easily design very high gain antenna. Not only that, already we learned some circuit components like let us say filter, coupler, where we use properties of transmission line. So, typically length is given in terms of lambda g. So, for these components, then the size at millimeter wave frequencies, it becomes very small. So, very compact component can be developed, and as a whole millimeter wave system, it will occupy small volume. So, typically potential applications, very high resolution radar, communication links even more than 10 Gbps. Now, people are talking about 5G wireless communication, and 5G wireless communication, nobody knows what will be the final frequency, but obviously it would be at millimeter wave frequencies due to these advantages of millimeter wave frequencies. So, next we will see the phase transmission equation. Let us consider we have one isotropic antenna which is radiating a power Pt in all the direction. So, that means this directivity is 1, or in decibel scale it is 0 dB. If I consider a spherical surface and let us say that isotropic antenna is placed at the center of that sphere, then average power density on the spherical surface, it can be given as Pt divided by the total area of the sphere. So, Pt by 4 pi r square watt per meter square, where Pt this is the transmitted power. Now, power density radiated by antenna with gain Gt. So, in this previous example we considered isotropic antenna. Now, if the antenna it has some gain, in that case it will direct the beam in it will direct the energy in a given direction. Higher is the gain, then it will direct more in that direction. So, obviously we will be having higher intensity in that particular direction. So, then S average in that case, considering antenna gain Gt, this is equal to Gt into Pt by 4 pi r square watt per meter square. Now, let us consider we have a receive antenna of effective area AE, and it is placed on that spherical surface. So, since its effective area is AE, so we can receive power PR AE into S average, then in expression it is Gt Pt AE by 4 pi r square into W. Now, receiver antenna, it is associated with some loss obviously. So, that loss term it is included in the antenna parameter gain. So, better to use the antenna parameter gain for the receiver, let us say GR. Then we have a formula that relates the gain of the antenna with its effective area AE and the wavelength. So, we use that formula here, then PR it becomes AE into S average in terms of then gain of the receiving antenna, it is GTGR into lambda square by 4 pi r whole square into Pt in watt. The term Pt into Gt, we call it effective isotropic radiated power or EIRP. So, this receiving antenna, we assume that this is placed in the direction in which the transmitting antenna is sending its power most in the direction of the main beam of the transmitting antenna. So, we can simply consider that as if the transmitting antenna, it is transmitting an effective power of Pt into Gt in every direction like the isotropic antenna. So, that is how the concept comes, effective isotropic radiated power Pt into Gt. Then we can calculate the ratio of Pr by Pt from the previous expression. This is Gt into Gr by lambda 4 pi r whole squared. So, this is obviously an ideal scenario where Pr, this is the received power, Pt, this is the transmitted power, and Gt, Gr are the antenna gains of the transmitting antenna and the receiving antenna, and lambda, this is the free space wavelength, r is the separation between the transmit and receive antenna. Now, you see why we call it ideal scenario. In this expression, we assumed many points which may not be valid in practical scenario. For example, we are considering a single frequency component and representing it by free space wavelength lambda. So, this is true only for a continuous wave, but if we use any communication channel, it might have some bandwidth. So, in most of the problem, what we do then, we consider the midband frequency and calculate the corresponding lambda naught at midband frequency. Similarly, antenna has some polarization. Consider a dipole antenna. So, any electric field parallel to the arm of dipole antenna, it can receive, but if any electric field which is perpendicular to arm of the dipole antenna, it can't receive. So, here we are considering an ideal scenario where whatever power coming to receiving antenna, it is receiving all the power, or there is no polarization mismatch. Similarly, we are, let us say the transmitting antenna is connected to a microwave source, then from microwave source whatever power delivered to antenna, the 100% power is not accepted by antenna. Antenna has some input reflection coefficient, we represent it by S11. So, depending on its S11, some power will be accepted by antenna and some power will be reflected back towards the source. Next, antenna, when it is going to radiate, antenna it is a metallic structure, inside we may have dielectric also. So, it is associated with some loss. Finally, it is a passive components, it can't add any extra power. So, that is represented by antenna efficiency. So, finally, then the total power whatever is radiated by antenna, it is less than the power delivered by source. So, we did not consider all these conditions when we derived this equation. Now, so this is a simplified scenario. Now, we can represent these terms in decibel scale. In that case, it becomes a simple arithmetic addition and subtraction problem. So, received power, we can write down Pt plus Gt plus Gr all are in decibel scale plus 20 log of lambda by 4 pi r. So, this last term, you see it depends on the separation between the antennas and the operating frequency lambda. So, here are some more points which we did not consider while deriving it. First, r is much more compared to lambda, so that we can consider it as a plane wave. Then the antennas are unobstructed, no multipath propagation is there, no atmospheric scattering or attenuation effect is there. Then antennas, they are ideal, which I discussed, and are in right polarization. Bandwidth is narrow enough for single frequency consideration, this point also we discussed. Then this above conditions, it can be achieved only in free space or in anechoic chamber. So, anechoic chamber, that is why any antenna measurement is done inside anechoic chamber, where we do not have any external effect, we do not have any multipath effect, or we do not have any reflection from wall effect. So, let us then consider the effect of polarization and the input impedance matching. So, we have a more practical form of a Phillips transmission equation. So, PR by PT, this is equal to GT. Now, GT and GR, it is a function of coordinate system, it depends on theta and phi. So, if the antennas are not aligned in their maximum beam direction, then we can take their actual gain value in that particular theta or phi, and we can put the values here. Then lambda by 4 pi whole squared into, we are considering then the input loss because of the matching problem. So, 1 minus gamma t squared, this is gamma t is nothing but S11 of the transmit antenna, and similarly gamma r, this is the S11 of the receive antenna. So, and AT dot AR this whole square. So, it is giving the polarization vector multiplied by e to the power minus alpha r. So, alpha is the absorption coefficient in the medium. So, at least in this equation, then we have included the effect of polarization mismatch, the effect of atmospheric loss, the effect of reflection losses at the antenna terminal, and also we represented gain of the antenna as a function of theta and phi, and we can consider the actual values facing to each other. But what are the factors which we did not consider in this equation? First of all, we did not include any multipath effect in this expression. So, that is a huge problem, because if I again consider that wireless communication system, whatever proposed for 5G, now we have to model properly any indoor situation. We can use microphone inside any, we can use our mobile phone inside any room also. So, inside room we have a reflection from furnitures, wall. So, we have multipath effect, not from one single path, but from several paths, and it is really difficult to model this type of scenario, particularly this indoor scenario. So, what we do practically, we do some measurements simply and try to fit that measured data by considering a typical n values, which will give minimum RMS error. So, in that case then PR by PT, it is simply proportional to GT GR into lambda by r to the power n. So, n value instead of 2, it is determined experimentally, and typical value it can vary from indoor to indoor model to another indoor model, and typical values between 3 to 5, not 2, but higher than that. So, now we are going to calculate link budget for a given wireless system. Some power is, let us say, being transmitted by the transmit antenna, then finally what power we are receiving at the receiver side. So, the effect that mostly determine the received power is free space path loss. It is given by 20 log 10 4 pi r by lambda in dB. We got it from that Phillips transmission equation. And what are the other contribution? Transmit power PT. So, if I increase transmit power, what we expect? Receive power will increase. Next, transmit antenna line loss. we will be using some cable or something to connect the microwave or millimeter wave source and to antenna, and it is a passive device, that source that cable, and it will give some loss. So, let us say that loss at the transmitting site is LT, and if the loss increases, then transmitted power will be less and received power will be less. Transmit antenna gain GT, higher is the gain, so it will direct more power to receiver side. So, that is why its sign is positive. Free space path loss expression is given above, it is negative. If we increase separation, path loss will increase, received power will decrease. Similarly, if we increase frequency, that means decreasing lambda, received power will decrease. So, we have a negative contribution. Atmospheric attenuation, again we have negative contribution. Receive antenna gain, just like the transmit antenna, we have a higher gain, we have higher receive power, and then the finally receive antenna line loss. So, antenna, receive antenna, it is also connected to receiver by using some sort of transmission line, it will give you some loss which is LR. So, in decibel scale, then it becomes simply arithmetic addition subtraction problem. So, PR, this is PT plus GT, we are just following the sign. Now, for a given link, whatever power we are receiving, that should be more than the receiver sensitivity. Let us say the receiver sensitivity, it is given by a minimum power PR min. Now, depending, now again you see whatever power we are receiving at a point, it is varying with, it will vary with time due to fading effect, multipart effect and other effect. So, we have to maintain a margin over that receiver sensitivity PR min. We call that margin as the link margin, and it is given by PR minus PR min. So, for any given link, then we have to calculate this PR and we have to see that minimum link margin is being maintained or not. So, typical suggested values is 3 dB to 10 dB link margin for any given millimeter wave systems. Okay, so, we will take a break, then we will take a numerical value of link margin calculation. Thank you.